Hi everyone, and welcome back to the Blue Waters webinar series. My name is Maxim Belkin, and I'm joined today by my colleague Scott Lathrop, and I'm pleased that you found time to join us. Today I'm pleased to welcome Todd Gamblin. Todd received his PhD in computer science from the University of North Carolina at Chapel Hill. Currently, he wears several hats. He is a computer scientist in the Advanced Technology Office in Livermore Computing at Lawrence Livermore National Lab. He is also a team leader at Lawrence Livermore, where he leads the DevRAMP team. And finally, Todd is a project leader in the US Exascale Computing Project, where he leads the Software Packaging Technologies project. And today, Todd will talk about none of the above, but about the tool that he developed called Spack. You can find more information about our presenter and today's webinar on our portal. Before Todd begins his presentation, I would like to remind our viewers that you can post your questions to Todd on YouTube and in our Slack channel. Information on how to join our Slack team can be found in the sidebar below me. With that, Todd, thank you for being here, and take it away.
Okay, thanks. I'm going to talk about Spack today. Spack is actually one of the projects that we work on all of those different teams that were just mentioned. And so it's a project that's funded by a lot of different organizations now. I'm going to talk a little bit about the motivation before I get into all that. Spack's a package manager. If you haven't heard of a package manager, it helps to look at what software looks like today. So if you look at a typical HPC code now, this is Ascent. It's a lightweight in-situ many-core visualization and analysis tool. It's developed at Livermore. And you can see that when I say this is Ascent, I really mean this little rectangle over here. All of these other pieces in here, including Conduit, VTK, Python, OpenMPI, all of these are libraries that are required to run Ascent. And so really, when you talk about installing a piece of software today, you're talking about installing it and all of its dependencies. So things are getting pretty complicated. Now, this may look complicated to you, but Ascent is actually a pretty simple package in comparison to some others. So if you look at numerical libraries, like here's MFEM. This is a library for doing higher order finite elements, and it relies on a whole bunch of solver libraries. It also relies on Python. It can use MPI, BLAS, and lots of other libraries. And so the build complexity gets even higher. And then if you look at things like modern machine learning libraries like LBAN, this is Livermore's artificial neural net tool, then things are even more complicated. There are tons of modules in here. Some of them are in the Python ecosystem, some of them are not, some of them are written in Fortran, some of them are written in C++. It's really sort of, HPC is about integrating across different language ecosystems with lots and lots of packages. And so for a user, in a world where we typically distribute things from source, it can be pretty daunting to install any one of these things. If you were tasked with installing LBAN and you had to install every single one of these dependencies, you would be working for a pretty long time. Now, if you look at a full software ecosystem, like what we're developing under the Exascale project, it's even bigger. So if you're talking about all of the software that a particular community uses, it's something like 15 plus applications. I think it's actually like 25 now in the Exascale project, more than 80 software packages, 5 or more target architectures or platforms. Some are going away. KNL is sadly no longer with us, or at least it won't be soon. Laptops, GPUs, ARM machines, Power, Xeon, lots of different processors. There are many compilers that we care about. There's a lot of different programming models. And then finally, you may need several versions of each of these packages, plus external dependencies, because essentially there may be conflicts between the versions of the dependencies that some of these applications need and some of the libraries need. So you may need to build several versions for different configurations. So, this is up to 1.2 million combinations if you try to build the whole thing out. And of course, we don't do that. But in HPC, we like to optimize for performance. And so we want the freedom to build the stacks of dependencies for each of these applications. Often the build gets to be so complicated that we actually trade performance for reuse and usability. So we'll just stick with the build that works, or the build that works more places. rather than optimizing it for a particular platform. And so, we really need to make it easier to rely on other people's software and to make it performant. And so this is one of the motivations for Spack. If you look at how other operating systems do this or how other tools do this, say your average Linux operating system or your Mac with Mac ports, around 2013 when I started working on Spack, this is how you might have installed something on your Mac. You would say port install libelf, it would go and fetch the sources for that thing, it would build it, and it would install it. And then you would have libelf and you could use it. If you tried the same thing on a supercomputer for a typical supercomputing package, it would look more like this. You would download all 16 tarballs that you need. You'd start building. You would fight with the compiler, the make system, the configure, make install, all of that. You would get it building finally after you corrected a number of errors. You'd run the code, and then it would segfault. And you would have to start over from there because things did not work. And so doing this manually can be pretty daunting. Each one of these packages is its own archive. You have to configure the build system, and you have to tell it where all of the other packages live. So if you've used an HPC system, you're probably familiar with modules. You say module avail, you can see all the software packages available on the system. They manage your environment. And so, I mean, that's great. There are lots of people who spend a lot of time installing things and then building module files on top of that. But modules don't manage the installation. So behind every good module system that you've used on an HPC system, there's probably a team of people who has built all the software behind those modules and made them available to you. And so, one disadvantage of that is that you don't really have the freedom to go and install your own thing and integrate it in the module system. You can only use what's available. And and again, they don't handle installation. So building configurations on demand can be difficult. So containers are getting popular now, and these are a great way to reproduce and distribute an already built software stack. We're not trying to replace containers. They also encapsulate all the dependencies that a piece of software needs, but somebody has to build that container. And so I don't think you shouldn't think of Spack and containers as competing with one another. They're really complementary. You can use Spack to build containers. You can use Spack to build software on bare metal, and in the HPC world, the container build is not as simple as it might be in the cloud. You can think of a container as basically a snapshot of an application plus all of its dependencies. If you build that for x86-64 Linux, then you're pretty well guaranteed that that container will work across, x86-64 boxes with a Linux kernel. But on HPC, we do things like we swap in the system MPI. There are lots of dirty tricks that are done underneath the covers to enable containers to use the hardware. And so that basically results in HPC containers needing to be rebuilt or rebuilt for specific platforms more frequently. So you still do have to build the container and you want to automate that. So think of Spack as basically the complementary tool that can enable you to do that. So what is Spack? It's a flexible package manager for HPC. It automates the build and installation of giant DAGs of software like the ones that I showed earlier. And unlike other package managers, the packages are templated. And so users can very easily tune for the host environment or pick different build options or those things are available on the command line. It's flexible. It lets you install the same package lots of different ways instead of just one way. And so if you want to use Spack, you can just clone it from GitHub using this command, git clone https github.com spack, and then do Spack install HDF5. And that will install HDF5 and all of its dependencies on your machine. And then this is just this says get me HDF5. I don't care how you build it. But you also have control with Spack. So if you want to build HDF5 in lots of different ways, we have a flexible syntax that enables that. And I'll talk more about this in subsequent slides. So just for an example, some of our code teams at Livermore have started using Spack. The Aries team was able to reduce their porting time for new platforms from 2 weeks to about 3 hours to get all their dependencies built. Previously, it was a very manual process. That's basically the time it took for a human to go and find all the different dependencies and packages they needed to build, versus the time it took for Spack to automate a pre-built, or a pre-packaged configuration. And then similarly on the Summit supercomputer, so that's the #1 in the world right now, they have something like 1,300 packages that they deploy on Summit. And we were able to reduce their build time, or at least using Spack, they reduced their build time from 2 weeks to about 12 hours overnight to build all of that stuff. And that installs the packages, it deploys the modules, the modules they don't have to write them by hand, they are templated based on what the Spack packages do. And so this reduces a whole lot of manual labor for different teams. It's also used by teams across ECP to accelerate development, and I'll talk a little bit about that later. So if you think about who can use Spack, it's not just big teams. It's end users of HPC software. So if you just want to install something on an HPC system that you happen to have logged into, you can use Spack for that. If you're an application team and you want to manage your dependencies in a controlled way, you can use Spack for that. If you want someone else to use your application, so if you're a developer of a library or an application that you want other users to be able to use this way, you can distribute your software using Spack. And then if you're a user support team at HPC centers, then you can use Spack to deploy the software stack that you would otherwise build by hand and then write the modules by hand for. So it's useful in a lot of different use cases. And I mean, we're trying to build a package manager that spans all of these different parts of the HPC ecosystem. And I think HPC is somewhat unique in that I don't think that all disciplines have this many different roles in their ecosystem. So Spack is used worldwide. There's over 3,500 software packages in Spack right now. We have over 2,000 monthly active users on the doc site, and that's been growing. And importantly, we have over 450 contributors. So there really isn't a barrier. If you want to get your package into Spack, you can definitely go to GitHub and submit a pull request and get it into the distribution. We encourage that. And so these are the places where we've seen visitors to our doc site for a month all over the world. This is showing the number of users in any given place. The size of the circle correlates to the number of users. And so you can see that it started to be used in a whole lot of places all over the world. This is active users on the doc site. You can see that since 2017, it's over doubled. And so every month we have over 2,000 people who visit the documentation site. I don't really have hard numbers on how many users there are worldwide, but this is the number that are browsing the doc site. And so I think that's a pretty good proxy for people who are actually engaged with the tool. Like I said, it's being used on HPC systems, and so in addition to the smaller sites worldwide, it is the official deployment tool for the Exascale Computing Project. I think you may have heard some about that last week at the E4S webinar. It's used on 7 of the top 10 supercomputers in one way or another, either by users or by the staff there. And then it's also had some penetration into communities outside of HPC. So the high energy physics community is using it to build a development environment for some codes that support, say, the Large Hadron Collider and some statistical analysis associated with that. It's used by the Astro team at Sandia, and then it's also been adopted by the Fugaku project, which is the big ARM SVE system that's going to come out at ReCAN, I believe, in 2021. And they're doing a whole lot of work to get all of our packages working with the new ARM SVE processor. So this is all pretty exciting. Like I said, anyone can contribute to Spack, and you can see here, these are some of the top organizations that have done so. And this also sort of shows the evolution of the project. So if you look at this, when we started working on Spack, say in 2013, I mean, it was just me. And I did this because I was sort of angry that I had to rebuild my graduate students' projects all the time. And, it gradually got more and more, robust, and we started using it in production at Livermore. And then in 2015, we actually presented Spack at Supercomputing. And so from then on, we really started getting contributions from outside people. We got contributions. So this top plot is showing the lines of code in packages. So these are the package recipes, and I'll get into what that is in a minute. But this is showing the contributions by organization. And so you can see if it was just Livermore that did this, that's this green line here. Today we've only written a small portion of the total lines of code in packages, and we wouldn't have nearly as much of a product if we did not have all of these other people contributing. So we're not even the top single package contributor anymore. This is actually someone from Argonne National Lab who's now a grad student at UIUC, who's this top blue line here. That's Adam Stewart. And then these other lines are other organizations and their contributions to the packages. As far as the core tool goes, the actual package manager itself, we still do most of the development there. I think we're slightly over half. But we've had a lot of help from other organizations like EPFL, Argonne, UIUC, Fermilab, like I said, Kitware. There are lots of people contributing to the core as well. So, if there's something that you want in Spack, I think do not be afraid to get involved and try to contribute the features that you want or the packages that you want. This is not the first tool to automate HPC builds. There are other tools, the so-called functional package managers, that do some of this multi-configuration building that Spack does. They do it in a slightly different way, and I would say, like Nix and Geeks, they allow you to build anything, but you have to hack on package files to do it. Whereas Spack packages are templated, and so they give you more freedom at the command line to build configurations that you need for HPC machines. There are build from source package managers that you're probably familiar with from your Mac. There's Homebrew, Mac ports. There's things like Gentoo and BSD ports that run on Linux machines. I'd say the main difference here is that these are sort of, you can think of these as managing a single prefix like RPM or Yum would do, or APT, the Debian package manager. They're managing one software distribution, whereas Spack is sort of managing lots and lots of different builds of different things. And then in the HPC space, there's EasyBuild, which you may have heard of. It's probably Spack's closest competitor. EasyBuild supports multiple tool chains. They have, some of the customizability of Spack, but I would say that the thing that they don't have is the templating that I'll get into later. The packages are basically built for one configuration of a package, and you have to write different configuration files for all the different configurations you want to build. Conda is very popular for data analytics, especially in the Python world. It's a little different in that it does not build from source; it distributes binaries. I would say it's not targeted at HPC. A lot of people will use it for Python and HPC. They have some support for optimized binaries, but in general, if you use Conda, you're not going to take advantage of your system's MPI. You're not going to take advantage of all of the optimizations available on most of the systems that we have, because it's a binary package manager and they distribute kind of lowest common denominator binaries, except in some limited cases. So, those are reasons to use Spack. I encourage you to look at all of these other tools and pick the one that's right for you. But I wanted to highlight how we're different from these other projects. So I want to talk a little bit about how to use Spack now, because I think one of the best ways to get familiar with a tool like this is to just see how it's used in action. I'm going to start with that spec syntax that I described earlier. So the main thing with Spack is that on the command line, you can essentially call up configurations of your software on demand. So if you want to install, say, the MPI leaks tool, this is a leak detector for your MPI program that we developed at Livermore, and you just want it installed, then you can say Spack install MPI leaks like this, and that's unconstrained. And what that means is it just says, hey, Spack, I want MPI leaks, and I don't care how you build it, just get it installed for me. And so Spack will go and it will create some configuration of MPI leaks for you and then install that, including all of its dependencies. You can be specific if you want to. So if you know that you need a particular version of MPI leaks, you can say that. So you can say install MPI leaks at version 3.3, and the at means that's the custom version that you want. You can add to that. You can say, yeah, build it with this compiler. I need it built with GCC 473 specifically. And so if you use this %sigil, that will tell it to build with a particular compiler, and then the version syntax is similar for the compiler to how it is for the package. You can say Spack install MPI leaks with particular options. So if the package supports options like threading or other different build options, we'll talk a little bit more about that later. Then you can specify those on the command line. Those are exposed by the package author to the user. And then you can inject flags into the build, so you can actually build the whole stack with particular optimization flags. You can tell it to build for specific microarchitectures. Spack now knows which flags to use for particular generations of processors. So you can say, I want this built for Skylake or Ice Lake or Excavator or any of the other sort of microarchitecture names. And then finally, this syntax is recursive, and so you have control over not only the package itself, but its dependencies. So you can say install MPI leaks and use mpitch as the MPI, and this is the version of mpitch that I want, and so on. And so that gives you a lot of control that you maybe don't have with other package managers, and that you would only get by building by hand. But it's a lot simpler to type this kind of thing on the command line. Spack list will show you what packages are available, and so like I said, Spack packages are templates. And so you see here it says Spack list, and it says 303 packages here, but these days we have over 3,000. But these are the names of different packages that are in Spack. And so if I want to install, say, Pappy, this is the name, but I can add those version specifiers and compiler specifiers, flag specifiers, etc. to that to get particular configurations. And then once I've installed them, I can do a Spack find, and it will say, hey, you have 103 installed packages. These are all the different versions of the OS, and these are the different versions of the compiler that you have installed them with. And so these ones up here are installed for Red Hat 6, for x86-64, using GCC 447, so something really old. And you can see that each of these packages has a version associated with it in this view. One of the things that we do in Spack that is, I think, different from other systems is that when we install things this way, we RPath them. So what that means is that if you're familiar with LD library path, it's an environment variable that you set to tell the OS where to look for libraries. And so that's how applications typically find their dependencies. In Spack, we use something called an RPath, and so we basically build the dependency locations into the executable or the library itself. So when you install these things, and there could be lots and lots of different directories where things are installed, they actually know where their dependencies live, and they know where to find the libraries. So when you run things, they will just run, out of the box. You don't need to load a module. You don't need to do anything special to run the applications. They're RPathed. And that's important for things like the Intel compiler, which can be fairly complicated in later versions in terms of which standard C++ library they use, or later versions of GCC using a different version of libstandard C++ than the OS. It can get really confusing for users to basically wire all that up. And Spack does that inherently as part of building. So we also store a lot of provenance with the packages. And so if you want to see how any of these packages are actually configured, and I guess one thing I didn't mention back here that I probably should is you may notice that there are some packages that have two instances in these sections. So dyninst is installed with two versions, for example. There's a call path library here at version 1.02, and then there's another version of the call path library somewhere in here. Down here at version 1.02. This is because this is just a high-level view. This is not giving you all of the provenance that Spack stores about the packages. We actually know a whole lot about what gets installed. And so if you want to see, why is my software working with this version of call path and not with this version, you can query the full dependency provenance, and you may find something like, well, this one over here that was built with Clang 3.4 was also built with this version of Boost. And this one over here was built with a different version of Boost. And so the reason that your build is exploding is because those two things are ABI incompatible. And so you should build with one and not the other. So you have that information available to you. Spack remembers it. So if you do install a lot of configurations of software, what we used to do was install lots of different directories. We would give them like a name. We would have, Boost 1, Boost 2, Boost 2-special, or things like that. And then we would forget all this information. And Spack stores this stuff in a database, and it gives each configuration a unique hash that we'll talk about later. So Spack also manages the installed compilers in the sense that there's a configuration file where you can tell Spack what compilers are available for your system. You don't have to write this yourself. When you run Spack for the first time, it will go and search your path and your environment for compilers, and it'll generate a version of this compilers.yaml file for you. And then if you say Spack compilers, it'll show you what's available in the system. And if you want new compilers, for example, you can load the module for the compiler that your facility provided, say Spack compiler find, and it'll put another entry in the file for you. So in general, you don't have to configure this file. So given all that, now you've sort of seen how Spack is used. I'm going to talk about some of the core concepts in the tool in a little more depth. So most existing tools do not support combinatorial versioning, and what I mean by that is if you think about your traditional binary package manager, and we talked a little bit about this earlier, like Yum, APT, YAST, these all manage a single stack. So there's one prefix, say user bin or slash bin, those types of directories where all the software has to get installed. So there's one /lib directory, one user lib directory. If you want to install multiple versions of things, it tends to be hard on these systems because essentially you have to integrate it with that single prefix. And the OS distros tend to be in the business of managing one stable distribution over time. And so that doesn't give you as much choice as you might like in the HPC environment where you're developing software where you want to try out different configurations and you may want to build with different stacks. And port systems like BSD ports, Portage, Mac ports, etc., they tend to be similar. They just build from source instead of installing from binaries. It is true that in RPM-based distributions and a lot of Linux distributions, there let me gone too far. Let's see, the ops directory tends to be used for these sort of one-off installations of things. So if you have a custom version of the Intel compiler, or if you have a single version of a library, you can put it in /opt/name. But that you have to name the directory yourself. You don't have a lot of provenance associated with the library, and so it can be pretty difficult to manage lots and lots of versions. You have to come up with a naming scheme. You have to come up with ways to get those things built in lots of different ways, and so they're really not intended for managing combinatorial versions of packages. We talked about containers. They're good at snapshotting things. You can have different containers for different stacks, but again, within the container, it's a package manager much like this. So with Spack, we handle combinatorial complexity, and this is how we do it. So the Spack layout, the way that we install files, inside the Spack directory under opt, there is this hierarchy of directories. And if you think of the package, say MPI leaks here, MPI leaks depends on the call path library, it depends on MPI, it depends on dyninst, it depends on libdwarf and libelf. And they're related like this. This is one configuration. And so if you can imagine this with a little more metadata on it, like the compiler, the build options, and so on, we take that whole DAG, and a DAG is a directed acyclic graph, and we hash it to generate these unique identifiers here for the directory layout. And so every package basically gets its own directory in here for every unique configuration. And all we would really need for the directory name is the hash to make it unique. But we provide this architecture information and so on, so that it's more easy to browse the directory hierarchy for a human. And so, like I said, we embed our paths into binaries. So this MPI leaks directory, its binaries have pointers out to directories for the dependencies, like call path wherever it's installed, and so on. And so it knows where to find those, and it knows specifically where to find the hashes that it was built with. And so with Spack, you don't really have to remember what version of MPI or what version of a library you built with in order to run the library. Our philosophy is that you probably knew what you were doing, or at least the package manager knew what it was doing at the time that you built. But by the time you get around to running the program that you built, you may not be the same person who built it, and even if you are, you may not remember what you did when you built it. So you shouldn't have to remember things like this. So I showed some of this recursive syntax for Spack specs earlier. You can say Spack install MPI leaks with the Intel compiler at version 12.1, and that depends on libelf at 0812. If we dig into this a little bit more, we said caret libelf, and you can see here that libelf is pretty far down in the DAG. But one of the things we do in Spack is we guarantee you that within any one configuration, there's only going to be one, or within any one graph, there's only going to be one configuration of any one package. And so referring to libelf this way isn't ambiguous. If you say MPI leaks caret libelf, you mean the one that MPI leaks somehow depends on. And you can still constrain that. But the user doesn't necessarily have to know the structure of this graph to constrain the configuration. So if you know that libelf 0813 is breaking your package, you can say, no, I want 0812. And I want that installed exactly this way. So we give you that kind of control. And this also ensures that things built in the same DAG are consistent. So Spack tries its best to come up with compatible versions of the libraries, at least according to the constraints that we have in the package files. And it makes sure that the DAG is constructed in a way that you can actually build. We handle things like ABI incompatibility that I think are pretty necessary for HPC. So if you think about MPI, Boost, Fortran, C++ libraries, these are things that don't have stable application binary interfaces. And what that means is that if you take an MPI program, you can compile it from source with different versions of MPI, and it'll work fine. But if you compile that MPI program and you take the binary that you generated, and then you take that binary and try to use it with a different MPI, things explode. So if you've ever compiled something with MPitch and then found yourself running with OpenMPI, you may have experienced this and seen weird errors when your MPI runs. And that's a common build error for HPC users, and so we try to get around that with Spack. And so this property that you would only ever have one version of MPI in your DAG is useful. And in fact, we go a step further. We let you write a templated package like MPI leaks that depends on MPI. But MPI is really an interface, and there are multiple implementations of that interface. So there's MVAPitch, there's OpenMPI, There's MPIG. There are lots of implementations of MPI, and you can basically tell Spack using the same syntax to build with one particular implementation if you want. So if you want to build MPI leaks with both MVAPIG and with OpenMPI, you could say Spack install MPI leaks caret MVAPIG, and you could say Spack install MPI leaks caret OpenMPI, and if you want 1.4 or higher, that's what this means. You can put more constraints on that. You can also tell Spack to basically choose the MPI implementation as long as it provides, say, an MPI2 interface. So these virtual dependencies or these interfaces, they're versioned in Spack. So if you said Spack install MPI leaks caret MPI at 2, it would find you an MPI that supports MPI 2. This isn't typically what you would write on the command line as a user, but this kind of constraint is useful in a package. So if you know that your code depends on MPI 2 or higher, or MPI version 3 or higher, you can specify that, and Spack will basically enforce that it's only ever built with an MPI implementation that supports that version of the MPI interface. So let's talk about what's going on under the hood a little bit. Concretization is sort of the core of Spack. And when you write these spec expressions on the command line, so this is MPI leaks, depends on call path at version 1.0 plus debug, depends on libelf at 0.811, we call that an abstract spec. It's abstract because it's not a full build specification. It's only what the user cared about. It's the constraint that they said must be fulfilled. And so Spack takes that, that's what we call normalizing it. It basically fleshes it out into a full DAG here. And on that DAG, it puts the constraints. So you can see here, this is MPI, or MPI leaks, and it knows that MPI leaks depends on all these things, as we talked about before. And it knows that, for this call path dependency, you put this constraint at version 1.0 plus debug on it at the command line. It has to be at version 1.0, and it has to use the debug option. And then down here, for libelf, likewise, you have the 0811 version constraint. So that's an abstract spec. We run that through an algorithm called concretization, and that basically fills in all of the blanks. And it does that according to constraints like the ones that the user passed on the command line, but also constraints like this that exist in the package files themselves. So like when you write a Spack package, you can say, like I said, that your package requires MPI 3, that you require version something or other of a dependency, or that you require, say, HDF5 with the parallel option turned on, things like this. And so what that does is it sort of automates the detailed configuration process that a user would have to go through, and it does it in a way that sort of enforces consistency constraints across the DAG. And so this concrete spec it's fully constrained. This basically represents one version or one configuration of a package that you can actually build. And that is passed to the installation method in your Spack package. And we actually store that on disk in a spec.yaml file and also in another sort of database file. Where you can query what was installed. And so you do have detailed provenance available to you on the back end of Spack. We store all this, these details about how your package was built. If you want to see what concretization would do in advance, you can call this Spack spec command to basically say, what would happen if I said I want to build MPI leaks with no constraints. And you could put constraints here if you wanted to. It'll say, here's what you input, and here's the concretized version of it with all of its dependencies. And you can see here that, MPI leaks actually has a lot more dependencies than what I showed in my example. But, this is the more complicated version that Spack would actually output. And you can see that, the concretized version has a version. It has a compiler here. It has an architecture set to a particular value. So it's going to build for Darwin, El Capitan, x86, x64. And then, Boost has all of these options set. OpenMPI has all of these options set, and so on. So if you want to see what a Spack package looks like, this is a simple example. This is basically, every package is a Python class. And so Kripke is a sort of SN transport, deterministic transport mini app that we built here at Livermore. And it's a CMake package. So it uses the CMake build system. And it has these CMake arguments here. You just define a method called CMake args that returns the particular arguments you want to pass to CMake. And so here we're going to say enable OpenMP depending on whether this particular variant was set. Enable MPI depending on whether something was set. And down here, this is the install logic. So it turns out that Kripke doesn't have a proper install method, which that happens a lot with HPC packages, that the build system is screwed up in one way or another. But for this package, basically what we do is we make the directory for we make the prefix directory and we make the bin directory under there, and we just copy the executable into it in this case. So install this build artifact into the prefix bin directory. And so that's the build logic essentially. And then this stuff up here, these are basically the metadata associated with the package that tells the concretizer, what are the constraints? What do I need to know about this package in order to get it built? And so this is the home page. This is just for users to see. This is the URL where you can actually download the tarball. These are versions of Kripke, and so this is, Spack is smart enough to take this URL here. It can find the version in that and extrapolate a new URL from this version. You can also specify a URL per version if you want to, but for most packages we can extrapolate these kinds of things. And this is a checksum that tells you how to validate the archive that you downloaded. And so you have some assurance that you're getting what was intended. Basically, we will download this package, this archive, and we'll check that it matches this checksum, and so you know that it's the one that the author of the package intended. And then these are variants. These are the build options. So like the plus threads that I showed on an earlier slide, these are basically options that you can specify with Kripke. So it can have MPI enabled or disabled, and so this is the MPI option. It can have OpenMP enabled or disabled. And then finally, the dependencies here. This is a conditional dependency. It depends on MPI when MPI variant is enabled. And that basically lets you build, Kripke can be built either with or without MPI. And it depends on CMake, and it's only a build dependency. So basically what this tells Spack is that it should not inject the RPaths into the build. It's only going to use CMake at build time. And so CMake at 3.0 or higher, basically that just tells it what version of CMake it needs. And so when it concretizes this DAG, it will get a version of CMake that meets those requirements. And so that's pretty much it. This is a fairly simple syntax for describing pretty complex things. And I guess the main thing is that you can rely on other packages in Spack. So if you want to rely on all of our MPI implementations, you can just say depends on MPI, and we have packages for that. If you want to rely on CMake, there's a package for CMake. You can say depends on CMake at 3.0 or higher. And if there are other common libraries that are in Spack that you want to depend on, you can just say, well, I need those. And that ensures that when your package gets built, those things will have been built before. So just some gory details for people who are curious for how we actually do this. And the Spack build environment is fairly sandboxed. So essentially, there's this install process. For each dependency that we want to install, we will fork off another process. And inside of that forked process for the build, we'll set up a special build environment. And so to do things like injecting the RPaths, injecting flags, and things like that transparently to the person writing the package, we use a bunch of environment variables to sort of make sure that most build systems will find our compiler wrappers and that they can find the real compilers. And so essentially, we set up the environment so that CC and CXX, F77, FC, all of these variables that are fairly commonly used by build systems, they point to these special compiler wrappers that we have. And in fact, it's a little more complicated than this in the sense that we actually name these after the compilers that they point to, so we have special symlinks for them. But I don't want to get too far into the weeds. We also set these Spack CC, CXX, and F77 flags to point to the real compilers so that when you invoke this Spack compiler wrapper, it ends up calling this ICC, but it's able to inject more arguments to the real compiler. And then we set up common environment variables like CMake prefix path, library path, package config path, and so on, so that when you run tools like configure, they're able to find your dependencies automatically based on these environment variables. And then the other reason that we fork a process here is because basically every build gets its own sandbox. And so if you want to mess with environment variables, if you want to change the environment in your package file, you can pretty much do anything. It's pure Python. If you have a really special case where you want to do something other than some of our templates, you can code that up, and you can do basically whatever you want in the compile environment. So anyway, after we set this up and we run install, we're going to run the build systems configure or CMake script. We're going to run make, and we're going to run make install. And then these end up calling into our compiler wrappers because of the way that we've set this up. and those eventually evoke the real compiler in the backend. And so this enables us to basically swap compilers into the build. It enables us to inject things like includes, library search paths, and R paths into the build, and also things like optimization flags. And so you end up having a lot of control here. You could think of Spack, at some level, as a system for injecting compiler wrappers into builds, so that we can basically customize things that we otherwise wouldn't be able to. Okay, so just to talk about some of the more advanced capabilities of Spack, I mentioned virtual dependencies earlier in the context of MPI. If you really want to get into the details of Spack and see how we've templated some of the things that are hard about HPC builds, we have advanced features. And so virtual dependencies is one thing that we've sort of fleshed out a package interface for. So if you think about libraries like BLAS, well, if you think about just libraries in general, you may have a client that depends on some dependency. And so you may want to know something about your dependency, like where do I find my libraries and headers when configuring my package? And in the code for the dependent package, you may want to ask the dependency questions. And if you remember, in Spack, you can have multiple implementations for the same dependency. So if your package depends on something like BLAS or LAPACK, we can actually abstract the fact that behind the scenes, these BLAS and LAPACK dependencies are particular implementations of BLAS or LAPACK. So BLAS may be OpenBLAS, it may be NetLib's BLAS implementation, it may be Atlas, it may be something else. But in your package, you write the same code basically to refer to the libraries of that BLAS implementation. So you can say, hey, my LAPACK libs are spec sub LAPACK, and that gets me whatever LAPACK I happen to be building with, regardless of how it concretized. .libs.joined, and so that just says get me the libraries joined with semicolons, and this gets me the similar thing for BLAS, and then you basically have something ready-made to pass to your CMake arguments here. So if you have to pass LAPACK libraries or BLAS libraries to CMake, you can do that in your Spack package, and that hit the mouse, and that allows you to basically have one source code, basically a single source package for lots and lots of different configurations. And so this is pretty useful because there are a lot. If you've ever tried to link with LAPACK and BLAS, it can be kind of a nightmare because sometimes BLAS is bundled with LAPACK, sometimes the same package provides both. Sometimes you use different implementations for LAPACK and BLAS. So you might build with NetLib's LAPACK implementation, and you may build with ESL to provide BLAS. And those are separate packages. But in another configuration, you may build with NetLib LAPACK so that it provides BLAS, and then you're using the same package for both of these dependencies. So in both of these cases, so suppose you're trying to build this RPack NG package that depends on both LAPACK and BLAS. You can use this same spec sub LAPACK.libs and spec sub BLAS.libs expression to get the libraries for multiple dependency configurations. So essentially, we have, I guess, polymorphic dependencies through these virtual interfaces. That's just one of the things that we do at the package level to try to make it easier for to package authors. If you were to try to build these configurations by hand, you would have to sort of know that NetLib LAPACK was in one directory, ESL was in another directory, that the libraries for ESL are actually a different set of libraries than the ones for NetLib LAPACK's BLAS. They have different names. And so this is actually a lot to manage. But in our version, these LAPACK and BLAS providers can actually, their packages tell you how to find their own libraries and how to find their own headers, and that's provided through this interface. So there's more on this in the detailed Spack docs. I just wanted to give you a sense of what's possible in the packages. Okay, so that's kind of the gory details of what Spack does under the hood. It's a pretty capable dependency manager. It can manage lots of different configurations of packages, and I wanted to talk about what's new and what's on the roadmap for Spack. So essentially, the work of building something like Spack is a lot like building one of these HPC software distributions, or it's a lot like building one of the mainstream software distributions. So if you think about Red Hat, Arch Linux, SUSE, Ubuntu, CentOS, all of these are Linux distros. There's a group of people who curate the packages for them and make sure that they work together, and they spend a lot of time on that. Spack is doing essentially the same thing. We're crowdsourcing that process in the sense that we have a lot of people contributing to our GitHub repo. But it's a harder task because the HPC community is not really as mainstream. It's not as widespread as these distributions, and the hardware is often unique, as we talked about before. So we want to build on Summit. We want to build on an ARM machine like Astra. We want to build on Cori for KNL. And we'd really like to have some kind of stable distribution for those types of architectures. And so we're really trying to provide the automation required to build a distribution that would support all of those things. And so our strategy is really we want to enable Exascale software distribution on both bare metal and in containers. And we would like to be able to distribute optimized binaries so that you don't even have to build eventually. And so that's what a lot of the focus of our roadmap is on right now. We are trying to add new capabilities to Spack to make the packaging easier. So we're trying to add optimized builds and binaries that exploit the hardware. I'll talk about that in a minute. We're trying to add more workflow automation, and so this is sort of high-level stuff to help out centers to automate all of these Spack builds that they want to do. And we're trying to have strong integration with containers as well as for bare metal deployments. So we're working with ECP, and I think you saw that the E4S distribution, which I'll talk about in a minute, is distributed with Spack. Those folks are essentially doing that curation work to make sure that the packages work on the architectures that we care about. They're distributing containers, and we're hoping that they can distribute bare metal builds of those packages as well. And they're setting up build pipelines at all the facilities, and we're trying to integrate with all the security that's required to get Spack working at HPC sites, so that essentially we could have the facilities building packages constantly so that the users don't have to do it. We would basically have automated builds at these different sites. And we're also doing outreach to make people aware of this, so that this becomes a popular thing to do on HPC machines. But you can see here, essentially, we have the Spack packaging activity right now. We're working on build and deployment automation, both for the Spack distribution itself and at different HPC facilities. And then we want to take these same packages and make it possible to deploy them in bare metal or in containers. And we'd like you to be able to use Spack in both of those environments in much the same way. So one of the things that we've recently added to Spack that I sort of hinted at earlier is we've added a library to Spack that can detect and compare microarchitecture metadata. So in previous versions of Spack, if you were to install a package and you installed it for, say, x86-64, it would actually build natively for the machine that you're on. So if you, for example, built a package on a Skylake machine and then you tried to run that binary on, say, a Haswell, the Skylake machine would have AVX512 instructions, but Haswell wouldn't, and so it would fail. And so we didn't have enough labeling, really, to represent where packages could be run. And so we've added this microarchitecture support, and you can see what we support with Spack arch -- known targets. And we have names for all of these things that are probably familiar to you. So you can actually refer to Haswell, Broadwell, Skylake, Cannon Lake, all of these different generations of Intel chips, Zen, Zen 2 for the AMD chips, and so on, Power 9 for the Power chips. And you can specify that on the command line in Spack. So you can actually say Spack install LBAN target equals Cascade Lake. And so what that means is that whenever Spack is building a binary for you now, or building a piece of software, we know what we're targeting. And so we actually put that metadata on the binary. We know what it was built for, and we know what it's compatible with. So if you build on a Skylake, we know that can run something from Broadwell, but not the other way around. And likewise, we know that if you built for x86-64, you can run that on Zen 2, but again, not the other way around, because this is the sort of lowest common denominator build. And so what we're hoping this will allow us to do is, A, distribute optimized binaries more broadly. So we could actually have builds that are optimized for a particular generation of hardware, and Spack can know to fetch the optimized build when it goes to install something. And that can be at the binary level, because we've labeled this in terms of the instruction set that's used in the binaries. We can also simplify packages. And so if you look through the Spack packages for some of the more complex packages, like OpenBLAS or anything that really wants to take advantage of the hardware, there used to be a lot of complicated logic around detecting what kind of chip it was building for, figuring out which instruction sets to disable or enable, or it would just punt that and give it to the user. It would have a bunch of options for whether you want to enable AVX512, SSE3, and so on. And that could get complicated. So now what we do is we're simplifying the packages by trying to remove all of these very architecture-specific flags And we basically use the fact that Spack knows what architecture we're building for. So in OpenBLAS, what used to be a complicated nest of if statements and user-supplied options is now just, if this target supports AVX 512, then enable AVX 512. And you can basically ask simple questions like this of your target architecture and figure out what features are available in a common way. And you may say, well, you could just look at proc CPU info. It turns out that that's complicated too, because the Linux machines, they will tell you what features are available on the architecture, but some features subsume others. And so like for AVX 512, there's actually a whole lot of different feature names for AVX 512. You have to know what version of AVX 512 you want to run. Or for SSE3, that's a common set of it's a common instruction set extension. If you want to ask your processor whether it supports SSE3, though, you have to know that on newer generation processors, the feature list only includes SSSE3, which subsumes SSE3, and you have to know that those things are related. We've simplified that now, so you basically just say, does it support SSE3? Okay, add the SSE3 option. Does it support AVX 512? Okay, add that option. And so the packages become much simpler. You're basically translating between that concrete spec that we give you out of the concretizer and the build system options, and you don't have to do a lot of complicated logic in your packages. Okay, so another thing that we're trying to do is we're trying to make Spack a little simpler to use in the sense that other systems like pip and conda support something called a virtual environment. We want it to be possible for users to basically have one file, say a spack.yaml file, that lists all the packages they want to install in one environment, and then basically they activate that environment and they get all those things in their path. And so this is the spack.yaml. It's fairly simple. You can say Spack, you can say include these types of configuration. You don't have to do this. And then you just provide a list of specs. And if you have this in a directory, you can cd into that directory and you can say Spack install. And it will basically install all of these things for you. And it spits out the concrete version of those specs into in what we call a lock file. And this basically says exactly how we built the package. So it says I built with this version, I built for this architecture, I built with this compiler, and so on for that package and all of its dependencies, for basically everything in the environment. And so you could hand another user either the spack.yaml file or the lock file, and they could basically reproduce your environment. If you hand them the YAML file, it's abstract. They could go and rebuild the same set of packages for their platform. If you give them the lock file, it's basically it's exact. You could reproduce the same build on the same platform with a higher degree of precision. And so this is a way that you can basically ship around portable environments with Spack. It turns out that this is actually pretty useful for building containers. And so if you think about the container environment, like I said, it's kind of it's a single prefix, or it's a single path that the user's invoking applications from or using libraries from. And so you basically specify what you want in there, and you might have a build that looks like this. So if you want to do a Docker build with a Spack environment, you could have a directory, say Spack Docker demo, with a Docker file and a Spack.yaml. And in your Spack.yaml, you might have some specs. You might say, I want HDF5 at this version, I want OpenMPI built this way, and I want the Nalu application. And then in your Docker file, you would just say, here's the base image. We have some base images on Docker Hub for Spack that you can use that have Spack readily just on the thing if you don't want to clone it. And then you just say, this is my work directory, copy the Spack.yaml in there, and run Spack install right there. And you can build that with Docker. You could run it with Singularity or some other tool on your HPC machine. Essentially, this is a very simple way to create an environment for an HPC application if you get it into Spack. And again, like this Spack.yaml format enables us to version this kind of configuration in a directory. So this could be a repo that you update over time, or this could be your Docker file build context. And this container can be repeatedly rebuilt on the system as things change. So if the OS upgrades or something, and there's a new MPI that's not compatible with the one in your container, you can rebuild the container pretty quickly. Or if you want to just distribute a new version of your application or change the HDF5 version or something, you can version that in a repo and rebuild it on demand. We're developing a version of this, or this is in the latest version of Spack. It's a combinatorial version of these Spack environments. So if you think of a Spack environment as basically a single prefix or a virtual environment for a container, a Spack stack is a combinatorial version of that, where you don't just want to build one version of the packages in your container. You want to build a lot with a lot of different tool chains. And so what you can do is, it's the same format, at least at the top level. It's got this specs list, And then there's this new matrix directive that says, hey, I want to take the cross product, I want to take the Cartesian product of the lists here. And so I'm going to take, these packages in this list built with every combination of compilers and MPIs that I have on the system. And so here's the definition. You can say I want to build with these compilers. These are the MPIs that you want to build with. These are all just specs. This is all just the same spec syntax that we've shown elsewhere. And you can say these are my packages. It'll build Nalu with mVapIch and GCC. It'll build Nalu with mVapIch and Clang. It'll build Nalu with mVapIch and Intel, and so on through all the other combinations here. There's a conditional syntax so that you can sort of filter that by environment or by what machine you're on, things like that. And so this is pretty this is a pretty robust way to define sort of what your facility is going to deploy. We're working on upgrading our environment here at Livermore so that essentially all packages are deployed this way, and we have a versioned description of what gets deployed on the systems. And basically Spack takes this whole YAML file, concretizes all the specs in it, and spits out a log file that says this is exactly what you built in your facility environment. And then we can take that and use it to reproduce the environment, say, on a new cluster or on a new machine somewhere. The other thing that this does is you can put your module configuration in here. So I haven't talked about this much, but Spack has a lot of options that you can use to configure how environment modules are built from the packages it installs. So it auto-generates modules for all the MPIs, all the compilers, and so on. It can generate LMOD hierarchies. You can basically say, here are my core compilers. These are the things that I want in my hierarchy. I want it to be MPI and LAPACK in addition to compilers. And then I don't want hashes to appear in my module schema. And Spack will basically take all these packages that it installs, and it generates a module. It generates an LMOD directory tree for those so that you can load them on demand. And you can basically customize this however you want it for your facility. So we're trying to build something that supports the same degree of reproducibility, configuration as code, versionable configurations for people who deploy software at HPC facilities. We're trying to automate the role of that team of people who has to support software at your local HPC site. So, this seems great, but, if I have to build this all on the command line, this is a lot of specs. This is a lot of different package installations to run. I don't necessarily want to run that all in one go. And so one of the things that we've done is I'm also involved in the ECP continuous integration project. And for people who have not heard of this, essentially we're one of the obstacles to deploying continuous integration, which is essentially automated builds of your project that sort of are triggered by your development. If you version something in a repo, it tests every version of the repo. HPC centers are very strict about security. And so, identity management has always been a problem. If you were to get, say, GitLab or GitHub Enterprise off the shelf and try to use sort of or Jenkins even, if you can try to use the CI capabilities of that, the jobs that run under these tools, they all run as the same user. And HPC centers are very particular about maintaining user permissions. So if I put files on my machine at Livermore and they happen to be export controlled, I don't want other users to be able to access those files. And so we need separation between the users. So we've added features to GitLab under ECP that enable the runners themselves to run as whatever user actually pushed to the Git repo, or as a user that they're authorized to run as. So if you have like a project user for your team that you want the CI to run as, you can do that. And essentially when the user commits to GitLab, GitLab talks to Slurm. Slurm fires off runners that are running as this user, or as, like I said, as some user they're authorized to run as. And those runners can actually run on the HPC machine. And so what this enables us to do is we now have a CI system that gels with the security model that centers have. And so we're able to deploy this for all users at our site. So we're rolling this out at Livermore. Other ECP sites like Oak Ridge and Argonne are starting to roll out CI for users. And we really want users to be able to do more automation like this. So for Spack, this is beneficial because this gives us a pretty easy way to automate the builds that we want to do on HPC platforms. And so in addition to the stack syntax I showed earlier, we've added some GitLab integration so that you can basically generate a pipeline on demand. And so this looks complicated at first glance over here. This is essentially a stack up here. You're saying, here are my packages, here are my compilers, here are my operating systems I want to build for, and here's the matrix of specs that I want to build. And then this is a mirror where I want to upload all the packages once they're built. And then there's this new GitLab CI section here. And so what this basically says is, this tells you how to farm the concretized package builds out to runners. So once it resolves all the dependencies for these things, once it basically takes that cross product, generates all the things it's going to build, it's able to map those builds to particular runners. And so in this case, we're matching on the OS. And so we say the ones that need to be built for Ubuntu 18, we're going to run that in a runner with this tag using this particular container. And so, and likewise for CentOS, if we want to build for CentOS, we can run that in a runner with this tag using this container. And so this isn't really for average HPC users. This is for people who want to build a whole lot of packages. But this essentially lets you farm out the builds in a GitLab pipeline, and it looks like this. Spack generates all the dependency relationships between the builds that you need to do. It generates GitLab stages, and then essentially you can just watch this thing progress and watch the builds happen on the machine. And if there are errors, we actually support sending the progress reports and error reports and logs to CDash so that you can look at them after the fact. And you can look at them in the GitLab interface as well. But essentially what this allows you to do is if a center wanted to version their configuration over time in a repo like this, they could basically say, these are all the software products I want to install, and I want them built like this whenever I check into this repo. So if this file changes, or if the package files in Spack change, then this pipeline regenerates, things are rebuilt, and it basically automates the workflow that people have been doing to install things on their system for a long time. We talked about E4S at the last webinar, but all of this feeds into the E4S distribution that we're trying to build under ECP. And so, Samir probably did a better job of talking about this last time, but essentially there are different groups under ECP that are working on sort of groups of related projects. And so all the people working on math libraries have something called XSDK that they work on. They test, they develop, they package the thing, they build it, they test, and they deploy it. And so essentially they're doing this loop for their own incremental releases, and they ensure that all these packages can be built together. The Viz folks are doing something similar. The programming models folks are doing something similar. And then the E4S team that Samir's leading basically takes all of these builds and integrates them into one ECP-wide software release. And so that's at e4s.io, and also see the webinar from last week if you want to see more about this. But this is the kind of curation that we're enabling with this kind of automation. And so eventually what our hope is that if E4S succeeds and if we're able to do what we want to do and we get cooperation from the facilities, we could have per laboratory pipelines, or we could have pipelines on relevant machines that we care about across DOE. And essentially there would be these GitLab instances that are running the pipelines on the HPC resources. As the facilities requirements change or as users requirements change, they build new packages. We could have a public package repository where essentially we upload all the binaries that we build this way. And then Spack users could come along, and instead of having to build things from source like Spack will do for you now, we could have basically pre-vetted binary configurations that are optimized for these machines, these actual HPC machines, and the users can just install them. So ideally, if we succeed at this, users will be able to run Spack and not even have to build, at least for the common configurations. And they would still have the freedom, if they want to experiment with new configurations, to build on top of these binaries or just completely build something new. All of that's possible. So things we're going to focus on in the coming year. I don't want to get too far into the details here, but multi-stage container generation with Spack is something we're going to work on. We want to have a Spack container command that's smart enough to know that things like compilers and build tools like CMake don't need to be in the final container image that you build. If you build a software graph that looks like this, all of these red things are basically things that need to be in the runtime environment, and these green things are things that only are needed in the build environment. We want the container to just include these red things, and for you to be able to run sort of a minimal container on the platform. We want to automate that. Currently, users have to do that manually in their container recipes, and Spack has the dependency information it needs to generate those builds, so we're going to try to do that automatically. We want to continue working with the E4S team and all the facilities in ECP and all the people working on projects to harden the builds and to get CI working across all the packages in Spack. And we're enabling parallel builds. So, in addition to the GitLab pipelines that I talked about, we'd like to have Spack basically know how to just be run in parallel. So if you get on a cluster and you want to Spack install some large graph, you can get an allocation and say srun Spack install. It'll install the entire graph. We're working on a new concretizer that does some much more aggressive things with how it solves and what we can optimize for. I think this is going to be helpful for generating minimal builds, for basically optimizing builds for particular platforms. Right now, we use sort of a greedy algorithm in there for what is actually an NP-hard problem. We're looking at leveraging sort of modern SAT solvers and answer set programming tools to make the concretizer smarter. And then finally, we are working on improved dependency models for compilers. Right now, as you saw, the compiler is it's not a proper dependency in Spack right now, it's an attribute of the node. And that lets you mix and match compilers in a graph, but we're not really modeling things like libstandard C++, G++, and things like ICC's dependency on GCC, for example. We want to get more down into the runtime libraries and really model this stuff so that we are able to enforce ABI consistency across your installation, in a very uniform way. So we're working on that, and that's pretty much it. If you want to get involved, there's lots of ways. You can go to github.com, just look at the Spack repo. You can look at issues, you can look at pull requests, you can look at what's going on. Spack.io is sort of a hub for all the different pieces of the Spack ecosystem. There's links to the doc site there. And we have a very active Slack channel. So, there's upwards of 400 total users on the Slack channel. There's probably 30 to 60 online at any given time during the week. And so, if you want help on Spack, you can go to the GitHub repo, and there's information on how to automatically get an invite to our Slack channel. So definitely try that out. We have a mailing list. I would say that Slack is more active. But either of these will work. And then we're on Twitter. And then if you want to do, if you want to read the docs, we have a lot of documentation. It's back.readthedocs.io. And there's a full day tutorial there that you can work through in a container image yourself if you want to just learn how to use Spack in a hands-on way. We make basically all of our tutorial materials from events like conferences available there. And you can basically do the same tutorial that we would give live if we actually went to one of these events. So yeah, definitely join us, and hopefully see you out there on Slack or on GitHub. Thanks.
All right. Thank you very much, Todd. It was a very interesting presentation, and you covered a lot of... I learned a lot about actually Spack myself. So I have a few questions, and you actually answered quite a few of them. But nonetheless, I think some clarifications would be useful. So first of all, my first question was stimulated by that boost example that you actually gave in the beginning, where there was ABI incompatibility. So I was wondering if is there a mechanism in Spack that detects ABI incompatibilities? Sorry.
No, not right now. So what we do right now is we're conservative about that. So essentially, that whole guarantee that you only ever get one configuration of a package in a DAG, it ensures that basically everything in your build is going to build with the same boost. We do go and do things like we detect the version of libstandard C++ that your compiler uses, and we use that to sort of guide compiler selection to a certain extent. But really detecting ABI and understanding all of those constraints is kind of future work. It is something that I want to get into, but we haven't really gotten deep into that yet.
So those colors, like you highlighted, boost in red, were like your colors. Okay,
yeah, those are my colors. If you actually type Spack find, it will not highlight boost in red and say like, hey, this is the boost library.
Okay, got it. Thank you. So is there an infrastructure in Spack for HPC site-specific optimizations? And you touched on that, but I just wanted
yeah, one of the things that I probably didn't cover very much in this presentation is that there's a whole lot of configuration you can do with Spack. So you don't have to actually specify all of these things on the command line. There's a section in the guide called build customization, where you can add essentially some of these options to a packages.yaml file, which basically says, for this package, I want to build it with this compiler. I want to build it with these options all the time. I want to prefer these versions, and so on. And so you do have a lot of control over what actually, over how Spack concretizes things. You can also, in the environments that I talked about, if you do Spack env create foo, then in your foo environment you can actually add environment specific configuration for that. So you can have one environment that prefers Intel, one environment that prefers the PGI compilers, and so on. And you can work it that way. So there's a whole lot of customization you can do.
All right, thank you. My next question, and I will be honest, I have quite a few questions. So if I'm familiar a little bit with the Homebrew and Homebrew on Linux, so some of my questions, therefore, they have this flavor of Homebrew, essentially. So if I install two versions of the same package, how do I control which version is currently active?
So yeah, you can do that in a couple different ways. Like I said, we support modules and environments. And so like if you just take Spack out of the box and you install two versions of packages, they're not automatically put in your path like you would have with Homebrew. You need to activate an environment and install it into that environment if you want that. Or everything has a module file generated for it by default, so you can actually say Spack, Spack load that package, and it'll find the module for it and load that. So you can do it either of those two ways, where you pick and choose yourself, or you just use environments.
Okay, thank you. So my next question is also related to Homebrew and actually to modules as well. Do you think Spack will decrease the load on HPC support personnel? Because the reason I'm asking this question is the following. It looks like the target audience is HPC users. At least mostly, and who might or might not have enough experience to use the tool. So, given that we have an that your target, not audience, but target infrastructure is HPC in general, do you think that will help HPC admins and support personnel, or not?
So I guess I can talk about our experience at Livermore, which is that we're able to now tell users to go install certain things themselves, right? So like in the cases where the support staff has not installed things, we can just say, hey, user, go download this with Spack and use Spack to install it. If you want to try that version, we don't necessarily want to support it, but you can build it yourself. So that has decreased the load on the support team in a lot of cases. And I would say like there's an iteration process there, because at the same time we're moving our entire user environment deployment to Spack, and Livermore has historically been sort of a combination of RPMs and build it yourself in terms of how the HPC user support team deploys things for users. Right now we're sort of hybrid RPM Spack. We're going to go full Spack for the next edition. And with this build pipeline stuff, I think it will decrease the load on us, because it'll become very easy to add things for users. So if a user requests something to be installed, that doesn't mean that someone has to go and learn how to install that package. It means that we just add it to one of these YAML files and deploy it, or at least that's our hope. And I'd say Oak Ridge has seen that happen, because they do deploy their entire user environment on Summit with Spack, and like I said, that used to take them 2 weeks of manual effort to do every time they had to rebuild. And now they rebuild much more frequently, and they just do it overnight. So yeah, I think it'll decrease the load.
Right. Excellent. One other thing that I wanted to also emphasize is that modules, they target a single location where people just module load and stuff, and Spack and other package managers, they imply that user would do Spack install and then package. I was just wondering if maybe Stack should also incorporate a little bit of that Spack use or Spack load, and allow HPC admins load locally, build some packages locally, and allow users use these packages just by using that command. But that's probably
well, I mean, I can talk a little bit about that. So there's two ways you can do something like that. You can actually specify modules or specific paths on the HPC system as external dependencies. So if you look at the section on build customization in the docs, it says you can take your packages.yaml, you can tell Spack that mpitch is installed in this location. and you can give it information about that configuration. So you could say mpitch at 3.1 built with Intel compilers is here, and then you can tell Spack to use that as a dependency. So that's configurable. And then the other thing that we have is that if we have something called chaining in Spack, where essentially if the facility deploys their software with Spack, the user can actually just point at that instance of Spack and say, hey, use that for dependencies. The facility has already installed stuff there, and we call that an upstream. And so look for the section about chaining Spack instances in the docs if you want to learn more about that.
Okay, thank you. And my next question is, what is your approach to packagers that don't initially build or have some issues in them? Do you work with developers, or do you just hard code the hacks solutions into your like package files?
Oh, right. Okay, so there's if you look in the docs at the packaging guide, there's a section on patches, and so there's a number of ways you can do this. But I mean, essentially, like a lot of projects will say, use this patch. They'll just put the patch in with the package in Spack, and so there's a package.py recipe file, and alongside of it, there's a patch that gets applied, potentially conditionally to different versions of the package, depending on which ones work and which ones don't. So you can definitely include patches. You can even tell Spack to download patches from URLs. And then the other thing you can do is you can just write a method called patch in your package. And there are some primitives in Spack for doing things like filtering make files and stuff like that, where you can basically edit the files in advance of the build, depending on how Spack tells you to configure it. And I think one of the nice things about Spack is that kind of work is simplified somewhat in that, if you look at a lot of build scripts that we used to write before we had a tool like this, they would spend a lot of time saying, hey, is this version of this package installed here? Is this version of this package installed here? Is it this configuration or is it this configuration? And basically querying the environment. And that can get pretty complicated. Whereas with Spack, you're basically given the configuration that you're supposed to build. It says here, build this configuration. And you have the full information in the build script. And so you can just say, okay, am I supposed to configure it with this version of Boost or this version of Boost? Or, if it's this version of Boost, I want to patch. If it's this version of Boost, I don't want to patch, and so on. And so I think that kind of code for basically, prepping a package for a build for a specific platform becomes simpler with that logic done for you.
All right, thank you very much. So I have two more questions, but you answered one of them in your presentation, actually. And but I would still like to ask my other question. Can you talk a little bit more about package registries? How difficult it is to make Spack use them, like HPC site specific package manager registries.
Yeah, we don't have a registry per se in the sense that like npm or bundler or some of the other package managers have registries. I guess if you wanted to call something a registry, I mean we call it a repo. And so like with Spack itself, when you clone the tool from GitHub, it comes with a built-in package repository, and that repository contains basically all 3,500 packages that are built into Spack. It's got the recipes, and those tell you where to download things. So it's centralized in that sense, as opposed to some of the package managers, which will have a registry server and then a bunch of distributed repositories for the packages. And so if you want to layer sort of site-specific packages on top of the built-in Spack repository, you can do that. And in fact, like we do that a lot here. So at Livermore, we have a lot of export-controlled codes or codes that we've specifically modified for our site, things like that, where the recipes are different from what we might expect from an upstream, or where we just don't want to release the recipes. So you can make a local package repository. There's a section in the docs on that. You can do Spack repo create and Spack repo add, and that'll basically get you a directory that holds package.py files. And then those can be overlaid on top of the built-in Spack packages. So if you have a local code, say like our Aries code, it's an export-controlled code, and it depends on MPI. You can just say depends on MPI, and it can use any of the MPI packages that are in the main Spack distribution. It just layers on top of the built-in repo. And you can do that with multiple levels, actually. So like you could have a second layer of repos on top of you could have general use internal packages, you could have sensitive internal packages, you could have even smaller, one-off groups. So there are ways to basically layer, I guess, registries or repositories as we call them. Does that help?
Yes, thank you very much. That was a very thorough answer. So we don't have any more questions at this point. All right, so once again, thank you, Todd, for a wonderful webinar. It was very informative, and I actually learned a lot myself. To our viewers, our next scheduled webinar is actually next week on November 6th, and it is titled Introduction to NVIDIA Inside Compute, a CUDA kernel profile. It will be presented by NVIDIA staff, Magnus Strangert. I hope I pronounced his name correctly. With that, I would like to thank you all for joining us today, and we hope to see you in the next webinar.